Okay, so we now try to understand about the internal forces resultants in a bar. We'll eventually also distinguish between a bar and a beam. Okay, so let's begin with this. Bar is a member whose transverse cross-sectional dimensions are much smaller and when we say much smaller, I mean at least less than 10th than the actual length. Okay. So it looks something like this. And then let me draw this. This is the centroid of the cross section. This is the transverse cross section. And that area is S. This end is 1, this end is 2. This is the longitudinal centroidal axis. Let's see. Okay, so I mean the applications of bars comes in trusses which are built for say telecommunication towers of mobile and television and so on, and also bridges. So if you see the picture of a Howrah bridge, you will understand what a truss is. And so bars form the truss members. Okay, and they can also be like a beam or a column in construction sites and so on. So there are many applications of this. Okay, so a bar may be either straight or curved. May be either straight or curved. And when we say curved, it can be either in one plane or spatial or 3D. So normally when we try to define a bar, sorry, I should show this with a dotted line perhaps. So at any S, sorry, S was not the area in this, it was the position of this area. So path coordinates are coming in over here. So I'll just show it with this S, and then we have the normal, we have the tangential, okay, and then we have the binormal. This end can be S is equal to 0, this can be S equal to whatever L, capital L. Okay, so a convenient basis for a bar is this EN, ET, EB, okay, of its centroidal axis. So you can see that this dashed line is actually coming in from here, the centroidal axis, longitudinal centroidal axis. Okay, so for the purpose of designing meaning the bar should be able to say sustain a given amount of load. For this we have to find the internal force resultants. Okay, at any given point we should be able to find the internal forces, and what will that do? It will help us really somehow gauge whether that particular point will remain safe or not under the application of that load. Okay, and as you know, I mean, we find the internal forces by making sort of an artificial or a hypothetical cut, and then that other part of it becomes external, and that's where we use our ideas of mechanics which we have been learning. Okay, so what we do now is, I mean, look at this particular case. Okay, we'll make a hypothetical cut at this cross section, okay, transverse cross section which we have drawn, and I'll perhaps show it with a different color over here. Okay, this blue color, just to at the same time I should not hide the centroid. Okay, so it's in the center of it. Sorry. Okay, so let me do that. Okay, so this is C, and then I'll draw the other part also, which is something like this. Okay, so at C we have this Fr, the resultant force. Over here we'll have this minus Fr. Okay, we'll have this resultant moment Mr. We'll have a resultant moment minus Mr. Okay, and then you have this tangential direction Et. Okay, that Et is coming just from over here. Okay, and this would be minus Et clearly. Fine. So that is C clearly, centroid C. Okay, now what we have done over here is we have considered the internal cross section of bar into two parts. One and two. So this is the first part, this is the second part. Now then we have this coordinate S. Okay, so what you see in front of you on the screen is the so-called free body diagram. Okay, so let me just use another ink for all this. Okay, because we didn't really show the forces over here, I think I should do that. Okay, and then you have this forces like this, and you have this, and you have this, and you have this. Okay, so these were the forces which were acting on this bar, and I show them here as well. So this one, and on this we have, okay, Okay, so we have this so-called forces shown now in both the two parts individually, including the internal forces which have been shown using this hypothetical cut. Now this is called the positive face. This is called the negative face. Okay, we can see how it's defined. The outward normal to the face of the plane of the cut cross section part 1 is in the plus 80 direction. This is called the positive face. And in the other, the outward normal to the face of the cut cross section of part 2 is in the minus 80 direction, and this is called a negative face. So the internal resultant forces and moment resultant forces are Fr and moment is Mr. Okay, also it can be called SCR, moment due to a couple. Okay, so for the on the positive face we are showing it as Fr and Mr. On positive face, on negative face it will be minus of Fr and minus of Mr. Okay, so we will now use this basis which we have E, N, E, T and E, B to write all the vectors which we have just defined. Okay, so let's write this Fr in terms of this ET is equal to Ft ET plus Fn En plus Fb Eb. Okay, this would be equal to minus of Fr minus of Et hat. Okay, so Et is in this direction, minus Et is in the other direction, so you have Fr and minus Fr related. Similarly, Mr on the positive face, okay, that is equal to Mt Et hat plus Mn into En hat plus Mb into Eb hat. This is equal to minus Mr to minus Et hat Okay, so this is 4.13. Okay, so depending on which phase you are writing, we'll just write it in this way. Okay. So irrespective of how you write, for example, you write FTET, that means it's the tangential component of the force on the positive phase. Okay. And similarly, you have this minus FTET. Okay. That would be the tangential component of the force on the negative phase. But both of them are pulling forces, right? Whether it's on this phase or this phase, I mean, both of these forces will actually be pulling it. So we require some sort of a sign convention, okay, which does not help, which does not contribute to any confusion in this, for this 4.13. Okay, so let's do that. Sign convention. A force component Fi I is equal to Tnb, okay, or a moment component Mi is taken as positive if while acting on a positive phase it points in the positive direction the basis vectors and if while acting on the negative phase it points in the negative direction. Of the basis vectors. Okay. So this sign convention will not have any sort of confusion now, that if the component is taken as positive, that if it acts on the positive phase, it points in the positive direction of the basis vectors, and if it acts on the negative and acting on the negative phase, it points in the negative direction of the basis vector, then it is still positive. Okay. So that's how you have to take it. So if there is a component acting on a positive phase and directed in the negative direction of a basis vector, it is assigned as a negative value, and if it is acting on a negative phase and directed in the positive direction, then it is also assigned a negative sign. Okay. And this, what I'll do now is I can do that over here. So this first body for C, we have Ft, Fn, F B, this is C, okay, and this is MT, MN, MB. Okay, and then this is say FB, FT, sorry, FB, FT, FN, so again MN, MB, MT. So this is how we sort of show all them in a diagram. So what we want to show now with this definition, we want to show the positive directions. Directions are shown below. So say if you have something like this, FT, FT, this is axial tension. Okay, so this is positive because it acts on the positive face. This is the positive face. Okay, it points in the positive direction of the basis vector. Okay, that's why this is positive. And if this acts on the negative face, then it points in the negative direction of the basis vector. This is the negative face and it acts on the negative. So both of them are shown with a positive sign. Okay, similarly you can have say a shear force Fn, they are also positive because it acts on the positive face and faces in the positive direction. The positive direction over here is clearly normal, here it was tension, and the same, it acts on the negative face and it acts in the negative normal direction, hence it is positive. Okay, then you have say this as your MT, the so-called twisting moment. Both of them are shown positive. Twisting moment. And lastly we will have MN, and then MB and MB. So this is twisting moment, and then this is bending moment. Okay, so it is quite relevant to normally ask what is this variation. How does Ft vary with S? S equal to 0 at say one end. I don't know where did I show. S equal to 0 at one end and S is one point in the middle. So how does FTS vary like this? Okay. So this is the normal force. And then what Fn of S, shear force. It will also be FB of S. Okay, and then MT of S, twisting moment and bending moment. MN of S, MB of S, bending moment. So since all of them will be depending on what point you are, these are all called distributions. Normal force distribution, shear force distribution, twisting moment distribution, and bending moment distribution. Okay, so this we have to show this, and normally these are plotted like a diagram. For example, you have S and you have FT. How will this diagram look like, and so on. Okay, so that's what is important, and these diagrams are used to predict whether the bars which have been designed are actually capable of carrying the load which is intended. Okay, so a bar is named according to the predominant component. Of internal force resultant for example, when Ft is predominant, so if you have a tensile Ft, it's called a tie. If it's a compressive Ft, it is called a strut or a column. So most of the buildings are constructed around columns, and they are naturally under compression. Okay, so that's what you should have known before as well, but here you can now fundamentally look at these definitions. Okay, so this is a axially loaded straight member. Axially loaded. Okay, meaning the loading is along the axis. Okay, and then if you have a compressive Ft, okay, this is called an arc when it is transversely loaded. And if it's tensile Ft, this is called a flexible cable. Now coming to B, when Mt is predominant, okay, in that case it is called a shaft. Sorry, which when the twisting moment is predominant, it is called a shaft or torque bar. Shaft is more common, okay, commonly used. Then if components other than Ft and Mt are predominant, okay, then it is called a beam. So you do not have to know the next part as well, okay? At least now you don't have to know about beams, but I'm writing it in green, okay, just because perhaps at some stage it will be required. So if you have, say, only Mn and Mb are present, no other internal force is present, are present in a beam, then it is for pure bending, okay. Then if you have Mn, Fb and Mb, Fb, remember, was the shear force, and Fn are present, Fn was also shear force, are present, then for transversely loaded beam, transversely loaded beam, and then you can have Ft, Mb, Mn are predominant in a bar under axial compressive load. And transverse loads. So both of them have to act. Okay, this is called a beam column, somewhat of a hybrid between the two. So please visualize all of them, okay, before you move ahead. Now we have to eventually find the, before we find those distributions of the normal or the tangential forces, okay, sorry, where did it go? Normal forces or the shear forces, we have to find a way how to solve them, okay. We want to eventually get these distributions by making a hypothetical cut and so on, but let's see how we can actually do that. Again, just like any case of statics, we require the equations of equilibrium. Of a straight bar again, we are not going for a curved bar at this stage, okay. So let's first what I'll do is I'll write the relevant ideas in words, then show it in a diagram, and then show it with the mathematical equation. That way linking up is quite easy. So replace the external loads on an element of length ds of the bar by statically equivalent loads distributed over length ds of its centroidal axis. Okay, Let me now show that in a diagram. So if you have this as your centroidal axis, this point is say S, okay, this point may be S equal to S naught. So at S equal to S, so first of all let me just show all these sort of random forces and moments, okay, too many to write, but I'm just separately writing them for the sake of this, okay. So this is S equal to 0 and this is S. Now I want to write QS. This is the equivalent, statically equivalent force, and then you have this MS, okay. Then this is F naught, M naught, okay. So QS, I mean clearly in this case it will be in what, newtons per meter, and the distributed external moment would be M of Newton meter per meter, okay. So Q can be written, since it's a vector we have to write it as QT ET plus QS, sorry, not S, QN EN hat plus QB EB hat, and M has to be written again as MT ET hat plus MN EN hat plus MB EB hat. So this is 4.14. Okay. So other than this, it may also be, the bar may also be subjected to discrete external forces and couples. So one of them I have shown in detail, such as F naught and M naught at S is equal to S naught. Okay, so other than this you can also have, so at every given point you can have lots of them, but QS and M are the equivalent, statically equivalent forces and moments. Now let FR of S and MR of S be the internal force and couple resultant for positive phase. Remember the definition of a positive phase, okay? The tangential has to be positive. Outward tangent normal has to be positive, sorry, not tangent. Okay. So ET and EN. Okay. The outward normal to the face of the cut is in the positive ET direction, hence it's a positive phase. Okay, so let FRS and MRS be the internal force in couple resultant for the positive phase of the cross section at point S of the centroidal axis. So a distinction which is not really made clear to you at this stage is that these S, E, T, E, N, they are all in the deformed stage or the deformed configuration. Okay, there is also an option to take it in the undeformed state, but the convention followed in our text is that of the deformed state. So I'll put that for an exact description. We should refer all quantities. What are the quantities? S, E, T, E, N, sorry, E, B, E, N, Q, M, F, R, M, R, even F naught and M naught, okay, to the deformed configuration. Okay, I mean, and perhaps we will learn later about the Lagrangian or the Eulerian descriptions. So this is the Eulerian one, in which deformed configuration is taken. Okay, at this stage it should not really matter. I mean, you should just know that this is described in the deformed configuration, all these quantities which are written in front of you. It does happen. I mean, if you have the deformations are really small, then it doesn't really matter, and you can approximate, because the deformed configuration in that case is almost the same as the undeformed configuration. So all these quantities can also be written in terms of the undeformed configuration. This is the part which is important, at least at this stage. Though if you do not go into much detail into these, it's okay for now. If the displacements and deformations are small, deformed configuration can be approximated to the undeformed one, just because the deformations are small. One. Okay, so let's now take up a so-called straight bar. This is O. Okay, and then So I'll keep on adding on this diagram as I describe it more. Okay, so consider a straight bar. Okay, so this is a straight bar, not curved, with x-axis is along the centroidal axis. X-axis is along centroidal axis. There is a coplanar load consisting of QS and M. Sorry, QS, Q of X, I'm sorry, not X, Q of X and M of X, because I mean we have the X coordinate as the centroidal axis. So let me just now write what it looks like. Say you have something like this. So this is what is, say, this is Qy of X. Okay, and then you have this moment, okay, which I'll show perhaps in a different color. So this was M of X. Okay, depending on where you are on the x-axis, the value would be given. Okay, let me now just like pull in some A, C, and then this can be, I don't know, D, B, and then there can be, say, one point like this which is E. Over here we have Fy naught and M naught, okay, at E, and this is the place where x is equal to x naught or s is equal to s naught, remember. Okay, now Q can be written as Qx of I hat, and I didn't actually show, but these are all the so-called QX's. Okay, Qx. So Q will be equal to Qx I hat plus Qy j hat, and M over here will be very clearly M into k hat. This is equation 4.15. Okay, I mean there are also, when at x equal to x naught, just like in the previous case, we have this fx naught I hat plus fy naught j hat. Okay, and you have m naught k hat as the moment. So what we'll do now is we'll just sort of make a cut, hypothetical cut, and then we'll try to write the internal forces. Okay. So obviously over here a positive phase automatically means it's in the outward normal is in the I direction. Outward positive phase implies outward normal in I direction. So we would want to write the Fr as I. Okay, we are just following the definition which we had learned over here. Where did it go? This one. Okay, for this ET, which was a normal over here. Okay, so for the positive phase, let me just write out. Okay, so I is positive, so that would be what? N I hat plus S J hat. Similarly, M R I hat is equal to M K hat. Now again on the negative, which is minus I hat, so the outward normal is in the minus I direction. That would be minus N I hat minus S J hat. Okay, and MR minus I hat is equal to minus of M K hat. So N is the normal force, S is the shear force, M is the bending moment. So if you take this AB element, okay, between A and B, there is no external discrete forces or moments are acting. Okay, and then we will separately write out the part CD. So let this be equal to x1 C and D be equal to x equal to x2. So consider AB of the bar in which no external force or moment act. Okay, so let me draw it for CD part of it. I should at least try to draw it straight. So you have this CD part. So this will be what? X equal to x1, x equal to x2. Okay, over here we should have n2 of x, we should have a s of x2, and clearly we'll have a m of x2. Okay, over here we should have n of x1. Okay, this would be s of x1 and m of x1. So this is qy. Okay, m is this distribution for this. Okay, and then you have the qx's are shown with these horizontal arrows, and these show m's. Okay, valid for every place. Okay, now if you want to write the equilibrium equation, okay, for this segment, first write fx is equal to n of x2 minus n of x1 plus x1 x2 qx dx. Okay, this is 0. Okay, so in the x direction, similarly in the y direction, this would be s by s into x2 minus s of x1 plus x1 x2 qy dx is equal to 0. Now if you take this first equation, okay, you can write this in the form x1 by x2 dn by dx plus qx into dx is equal to 0, and you can also write this one, okay, just as x1 by x2 ds by dx plus qy dx. Okay, now again, I mean, the equilibrium equation doesn't end there. We have to also balance the moments about the z-axis, k-axis. So that would be mx2 minus mx1 plus x1 to x2 xqy plus m dx. They'll also be terms due to the shear forces. That would be x2 into sx2 minus x1 into sx1, and this would overall be equal to 0. So just think of this point as O, okay, and from here you are measuring, say, a distance x, which is x equal to x1 on C and x equal to x2 on D. Okay, this implies that x1 to x2 dm by dx plus dxs by dx plus xqy plus m dx is equal to 0. Now notice all these three values, I mean, you see all of them are equal to 0 irrespective of what you choose as your x1 or x2. So for all the above to hold true, for arbitrary x1 and x2, what should happen is, well, clearly the integrand itself must be equal to 0. Okay, and that's the so-called zero value theorem, or whichever way you would want to call that. So this clearly means that dn by ds is dn by dx, I'm sorry, dx is equal to minus qx, ds by dx is equal to minus qy, and dm by dx is equal to minus s minus m. This is equation 4.16. Okay, so one is that, I mean, this, to arrive at this from this one, you have automatically used this and this. Okay, you will apply a chain rule over here and so on. Okay, anyways, so once this is done, you can arrive at equation 4.16, and obviously we had made it very clear that there are no external forces acting on this segment, okay, AB, and clearly CD is within it, so even for CD there would be no external forces on moments acting. Now what you can do is you can eliminate S, which is the shear force. Okay, so that will give you d2m by dx square is equal to qy minus dm by dx 4.617. Okay, so if you differentiate this one with respect to x, you can utilize ds by dx from over here. Okay, so next is take up a very small part of it. Okay, this is from say x naught minus epsilon 1 to x naught plus epsilon 2. Okay, so this is a infinitesimal element of the bar. Okay, x naught can be any any x can become equal to x naught over here, depending on your point of interest. Okay, so this is the idea about this, and in this case clearly epsilon 1 will be tending to 0 and epsilon 2 will be tending to 0. So what you have to do is just call this as x1, call this as x2 in these equations. Okay, so x1 is x naught minus epsilon 1 and x2 is x naught plus epsilon 2. Okay, and in these limits the contribution of distributed loads and moments, distributed loads, which is what, forces and moments, is 0. Okay, because it is so small that as soon as you integrate it, it will be 0. Okay, now once you write say this expression for this case, you will get n of x naught plus, meaning it is x naught plus epsilon 2, minus n naught n of x naught minus, which is x naught minus epsilon 1 plus fx naught. Okay, this is the additional force which you remember we had given it. X equal to 0 was somewhere over here, this one. Okay, so we had this also had a fx naught and fy naught and m naught k. Okay, so that's where we are taking it. This is equal to 0. Similarly, you will have s of x naught plus minus s of x naught minus plus fy naught is equal to 0. And then you can have say m at e. So e was the point which x was equal to x naught. So at this point, m of x naught plus minus of m of x naught minus plus m naught is equal to 0. Then you have n of x naught plus equal to n of x naught minus fx naught. This also gives us s of x naught plus S of x naught plus is equal to S of x naught minus of Fy naught, and M of x naught plus equal to M of x naught minus M naught. So this is 4.18. So as you can see, these are 4.18 are so-called jump conditions of equilibrium. Jump conditions because the normal force and the shear force and the bending moment suddenly jumps. Okay, jump conditions. Of equilibrium. At x naught. So, and obviously the jumps are equal to these values fx naught, fy naught and m naught. Okay. So if you have a bar which is only under axial load, okay, then what you would have is only, say, this one, because there is only axial load, and this one, the first jump condition. So you would have only dn by dx is equal to minus qx, and n of x naught plus is equal to n of x naught minus fx naught. Okay. If again qx is equal to 0, then this equation will give us what? N is equal to constant, because dn by dx is equal to 0 then, so this will give a constant, and this is a situation which exists in a two-force member, two-force straight members. So meaning that if you go from x equal to x1, from x to x equal to x2, the normal force N remains constant throughout. Okay, so this exists as a two-force straight member, and it is very commonly used in trusses, which will be the next topic which we study. Okay, so if you look up the picture of any bridge or say a telephone tower or television tower, you will see a truss structure. Okay, it looks like this, what you see in the diagram in front of you. Okay, so we will try to study that and then try to see how we can find the forces at each element of it. So we design trusses based on forces in their members. If we know the overall load to be carried by, say, a bridge, then you would design it in such a way that the overall load is carried and none of the members of it fail. Okay, so we must find out what are the forces on their members. So what you have in this diagram is a bridge truss. Okay, you can also have a tower truss that just goes vertically up. You may have seen it around you. Okay, so the important part about this bridge truss is that the ends are connected to other members or to foundation. So this is the foundation, okay, and the other members, for example, these are the joints. So I'll just remove them now. So they are joined to other members or the foundation by bolts, which is a non-permanent joint, or a rivet or a weld. These are permanent joints, rivet or weld. Okay, rivet or weld to a gusset plate. So this is how the plate looks like. Sorry. So this is the gusset plate, and how is it? So there is this permanent joint like this, permanent joint like this. So these are all members, okay, joined together. So this can be, say, F1, F2, F3, and F4. So these are 4 members joined together using a gusset plate. Okay. So this is clearly a permanent joint of these members. So this may happen at a foundation or elsewhere depending on the need. Now the reason we model the forces, the reaction so called of this constraint, what is the constraint? The gusset plate over here, only as forces, is because of this. The members are long compared to their lateral dimensions. Therefore, they bend easily. And the gusset plate is able to exert very little rotational constraint on them. Therefore, the action of gusset plate on a member is modeled only as a force, not as a moment. Okay, so just because the members themselves can bend, okay, so the gusset plate is able to exert very little rotational constraint on them, okay, and hence I mean, if it was offering some sort of a rotational constraint, then we would have to take a moment of this constraint, but it's not, so, or negligible, that's why we are only taking a force. Okay, and this is valid if, for example, all of them meet at one centroidal point. Okay, this approximation is good. If the centroidal axis of the connected members are concurrent. Okay. So what we do is, in such a thing we try to model using, let's say, I'll show a diagram. We want to sort of draw the same thing. So let me draw that over here. Okay, let me draw that over here. So this is what F4, F3, F2 and F1. Okay, so we have this pin joint. So once the sort of reactions by the constraint, this gusset plate is only forces, okay, then we can model this joint, can be modeled as a smooth ball and socket joint. At the point of concurrence. Three dimensional truss, space truss, and as a smooth pin joint for coplanar truss. Plane truss. So in this diagram we have only shown this coplanar truss which can be shown as a pin joint. Of course, if it's a three-dimensional one, it can be shown as a ball and socket joint. It is not shown perhaps because it is harder to draw, but I think you get the idea. The important part is that it must be a smooth. Okay, because if it's not smooth, you know that there will be some constraint to the motion and then the moments coming in. That's something which we don't want. Okay. Now, what are the external loads on the truss other than the weight? Okay, so the external loads on the truss other than its self weight are transmitted to the joints by a system of floor beams and stringers. Stringers are the cables, such that the transmitted loads have a very small moments about the joints. Okay, so a truss is designed to support loads much greater than its own weight. That is obvious by the applications which you look at the bridges. Okay, so the weight of the members are usually small, so they are neglected, and that's why the self weight part is actually negligible. Okay. If you have to sort of take up the weight of a member, then you assign say half the weight of each member to the joints connected to it, and the member itself should be treated as weightless. So for example, if this is a joint, this is a joint, and for some reason you have to go for a more accurate analysis, then what you do is just apply half of the weight to say this particular joint from this and half of this from this, okay, and then assume the members to be massless. That way you can do slightly more, but I think we will not be doing that, so we don't require that accurate analysis at this stage. So let's summarize the definition of a truss in a more formal way. A framework, a framework formed by joining bars, these are the members, so that their centroidal axes are concurrent at the joints and their weight is negligible compared to the applied forces which act only at the joints. Is called a truss. So this is the exact definition which we have taken based on certain assumptions which we made, and we will stick to it very strictly when we deal with the analysis of truss structures. Okay. Okay, and as I have already repeated, two members are joined together, two or more members are joined together. First of all, if it's a coplanar, then it is like a pin, smooth pin joint, and if it's in a three-dimensional or a space truss, it's a smooth ball and socket joint. So the word smooth is important. The joints do not offer any rotational constraint. Okay. So this implies that all members are two force members with the forces acting along the axis or the line joining their points of connection. Okay. So let Fi, so because it's a two force member, it really makes the analysis part somewhat easy. So let Fi be the tensile force on the ith member at its end its every cross section is subjected to axial tensile force. Okay, so if you want to say draw the free body diagram of a joint, I'll show this over here. Say this joint at A, okay, you will have to just show these forces which are acting axially, okay, because these are all two force members, and remember the notation of 1, 2, 3, 4, okay. So let me draw that over here. This is the joint A. There was a force P, F1, F2, F3, F4. Okay, so always show them as a pulling force. Show them as a pulling force. Obviously, if the answer comes out to be after you apply the equilibrium equations and then the answer comes out to be negative, okay, in that case you can just reverse it, okay, then you can just know that the actual force is not pulling but it is compressing, okay. So if actual answer is negative, then assume to be then it is compressive. So if it is forces are pulling, then you call it a tension member. Forces on a member, okay, member are pulling, then you call it a tension member or a tie. If it is compression, then you call it obviously a compression member. A strut. So you just have to look at the forces at the ends of the member. One of the things I sort of forgot, I mean I just told you about the idealized joint, okay, but you can also have an idealized support. Okay, this would be like, sorry, say a roller like this and this. So this means that this particular support is only allowed to move in the horizontal direction. It offers no resistance. It does not allow a rotation. It does not allow movement in the y direction. So it can freely slide on this x-axis, okay. Similarly, you can have supports like this, okay, or you can have this sort of a. So in your examples you will see all of them and perhaps understand it much better. Okay. Okay, so I mean, just to forgot, this should be a sort of a roller joint, a roller sort of constraint. It is a rocker, okay, and this is a slip joint. So the reason you require such sort of supports is to allow a provision for contraction or expansion due to the temperature change at the support. Okay, so if you have, for example, a support over here like this, okay, and because of the temperature change, you have to allow for a compression or contraction depending on what is happening to the temperature, increasing or decreasing. And then that can be done by this sort of a support. So if you don't have supports like this, if the truss does not have a provision for either of them, like roller, rocker and slip, then they are usually statically indeterminate. You will see that. Okay, I will put that in green for now. Trusses without a roller, rocker or slip joint are statically indeterminate. Okay, now let's try to study this from a degree of freedom perspective. Degree of freedom of a truss. So at this stage, please go and revise what were the degrees of freedom, and you should pause the video right away. Okay, now if you have, say, a truss contains B rigid bars. B is the number of rigid bars. It is connected at J joints and with C foundation constraints. Okay, so the J is the number of joints and C is the foundation constraints. So you can see this over here. Let's see how many members are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So B should be equal to 11. Just check this, okay, I may be wrong. It has a J joints. So what are the joints? 1, 2, 3, 4, 5. Okay, so J is equal to 5 and the constraints are 2, 1 and 2. Okay, so that's how you count it. We'll do more examples of this just to get started. Okay, so what are the number of constraints which you need to specify the J joint? So each joint will be represented by 3 coordinates. Hence, if you have in 3 dimensions, and if it's a 2 dimensions or plane stress, it would be 2J. So number of coordinates needed to specify the positions of j joints is 3j, okay, and it will be 2j for a plane truss. So just because we want to learn about trusses, we will assume 2j henceforth, okay, just so that we keep it as a plane truss throughout. Now there are b number of rigid bars, and the coordinates must satisfy those b constraints, okay. So the coordinates must satisfy b constraint equations due to fixed lengths. Lengths of b bars. So say if you have a bar AB, then what are the coordinates? Well, it should be xa minus xb whole square plus ya minus yb whole square plus za minus zb whole square is equal to the length of this bar, okay. And C constraint equations, C constraint equations, okay. So I mean the lengths, the coordinates of the joints, okay, the coordinates of the joints are also the coordinates of the ends of the bar, okay, hence they must satisfy first of all this, and for every bar you can write one equation. That's why it is said that you have B constraint equation. Then it must also satisfy C constraint equations due to foundation. So example, xa is equal to 0, yc is equal to 0, okay. And hold on, x a is equal to 0, okay. So what is this constraint? That the y coordinate of the constraint is 0, because I mean it's not allowed to move in the y direction, okay. So that's one example, and similarly you can have the x constraint of a will also be 0, x coordinate of a will also be 0. So you can look all that over here, okay. So you can look in this truss, and for A you can say this. I mean this is just an example, but you can see this, okay. Now let n be the degree of freedom of the truss okay if all the constraint equations are independent, then if all constraint equations are independent, then n is equal to 3j minus b minus c, else n is greater than 3j minus b minus c. Okay, so 3j, I mean we are writing the most general form and then subtracting the conditions which we already have. One is this b and then the other is the constraint c. Okay, the degree of freedom of the truss is equal to this if all the constraint equations are independent, and if they are not independent, clearly the n will be greater than this number. Okay, so the gap would increase then. So for each joint, and we know when we say joint, it's a smooth pin joint. Okay, for trusses, there are three equilibrium equations. Okay, one in the x, one in the y, one in the z direction. So for each joint, you will have three equilibrium equations. That means the total you will have 3j equilibrium equations for concurrent forces at j joints must involve B member forces and C foundation reactions. Okay. So if you take the equilibrium equation for the whole truss, I mean for example if you consider the whole truss as your system, they will not furnish any independent equations. This is something which we have already also discussed before, okay, when we were considering the system of rigid bodies. So that is obvious from there. Now the necessary condition for a truss to be statically determinate is that the number of unknowns b plus c has to be smaller than or equal to 3j, okay, because you have only 3j equilibrium equations. Okay, so if you have, say, if you want to arrange all these equations as a system of linear equations in a matrix form, so A will have a size of 3j cross b plus c, okay. F will have what? Will have b plus c. These are the so-called unknowns. So this is in a vector form clearly, and p of 3j is the load vector. So this is coming from your linear algebra, and you should verify it from your understanding of that course if you have already done it at this stage. The solution exists if rank of A is equal to rank of A comma B is equal to B plus C. So this is the necessary and sufficient condition for truss to be statically determinate. You should know how to find the rank of a matrix by this stage if you have done the course in linear algebra, and it is a first year course, so it should have been done. Okay. So just based on this number n if you remember is the difference between this 3j and b plus c. So n is equal to 3j minus b minus c. So based on this number n, we have some classifications of what this should be. Okay. So two types of trusses truss. One is the so-called rigid truss. So let me just write n is equal to 3j minus b minus c. Okay, this is when n is equal to 0. So the necessary and sufficient condition for a fully constrained rigid truss is n equal to 0. This implies that 3j minus b minus c is smaller than equal to n, which is equal to 0. That is 3j is smaller than or equal to b plus c is a necessary condition but not sufficient. And that comes from over here. We had claimed over here that, where did it go? The necessary condition for a truss to be statically determinate is that the number of unknowns b plus c must be smaller than 3j. Okay. So you can have, based on this, over rigid truss and b plus c is greater than 3j. So it's called over rigid if removal of a few members, and you will see all this when you see the solved examples more clearly. Okay, a truss is called over rigid if the removal of some members, I mean it can be one member also, or some foundation constraints still leave it fully constrained. rigid truss. This implies that there exists at least one dependent constraint equation This implies 0 is equal to n greater than 3j minus b minus c, or b plus c greater than 3j. This implies statically indeterminate. So this is all, the language of this is coming all from linear algebra. So you must be very clear about the concepts of linear algebra. Otherwise all this will seem like some sort of a alien language, okay? So please be very clear about the concepts of linear algebra while you see this, and it should be very clear about it. So b plus c smaller than 3j was for the condition for statically determinate. So b plus c greater than 3j will be the condition for statically indeterminate. Okay, so that member which can be reduced, that member which can be removed, okay, removal, that is called a redundant and the corresponding truss is called internally redundant. Externally redundant. Okay, respectively. So what happens is that if you have, say, 10 members in a truss and you have 3 redundant members, okay, so even if, say, these 3 members sort of fail, okay, or break, then the truss would still be safe, okay. So that's why these redundant members are used, because in a practical situation any member can fail due to one reason or the other, and hence these redundant members help you sort of minimize the risk of the overall failure of the truss, because if these redundant member fails, it's okay, they were anyways not contributing statically to the truss, okay. So let me show that over rigid structures, over rigid truss. So we have 1, 2, so this is there, and we have this member which is, I'm showing like this just so that it does not really intersect with this one. So we have this as 1, 2, 3, 4, 5, 6, 7 and 8, okay. And let me show this another one as well. So this is what 1, 2, 3, 4, 5, 6, 7. Okay, so this one. So we're drawing similar ones so that they are easy to relate. Okay, since the purpose is to understand at this stage. And then we have this similar one. So let's call it 1, 2, 3, 4, 5, 6, 7, and 8. So I hope you can see the constraints and the members and the joints in all three of them. Okay, so the over rigid trusses 1, 2, and 3, which are shown, are this is 1, 2, and 3. Are, first of all, you have to verify that they are over rigid, and you know the way to do it. Verify over rigidity of 1, 2, and 3. Okay. So they are redundant internally. So member 3 or 8. Externally redundant, the constraint 4, okay, or both. So you can have member 3 or 8 and C is equal to 4. Okay, so you should know exactly what is C equal to 4, say over here. Okay, I mean, what is the fourth constraint in this one, which is redundant externally? Okay, externally meaning, I mean, not in the members but in the constraints, and internally redundant being the member which can be removed. So you can do that, and it holds a very powerful sort of idea in the problems of truss which you will be dealing with. Okay. So about this one, there is another note given in your text, so which I'll put in green. Redundancy of the type shown in truss 1, this one, allows a tensile bracing using cables for members 3 and 8 instead of bars. So you should know the difference between a bar and a cable by this stage, and because they are redundant you can just use cables rather than bars. And a cable, as you know, cannot sustain a compressive load. A cable cannot sustain a compressive load. The problem is statically determinate. As either F3 will be equal to 0 or F8 will be equal to 0. Okay. So that, where did it go? That at least one dependent equation, I mean that one gap is now filled. Okay. This was causing this a static indeterminacy, and now if a cable is put in, then it becomes statically determinate over here. Okay. Now the second sort of variant in this is the just rigid truss. You have n equal to 0 and b plus c is equal to 3j. Okay, so a truss is called just rigid if the removal of any member or foundation constraint makes it a mechanism. Okay, things start to move relative to each other if you remove any member or a foundation constraint. Let me show that as an example. Okay, so you have this. B, A, C. Okay, and then we can show another one perhaps over here. Oops, there's one more. Yes. A, B, C. P. Okay, it's P on this one as well. Okay, so these two which you see in front of your is the they are just rigid trusses. So first thing which you must do is to verify that it is just rigid trusses. And how to check that? You just have to see whether these two conditions are satisfied. Okay, this is a statically determinate, and this is not statically determinate. Okay, so this is what A, B, and C. So if you want to say focus on this over here for this B part, okay, let me draw that separately. So the original position in B and obviously final, so this is moved over here, so let's call it B dash, and then this is C, this is A, okay, and this is B. This angle is theta. Okay. This is what F and F. So for this, I mean, because it's statically indeterminate, this one, the equations of equilibrium of joint B of this one, okay, can be satisfied only in deformed configuration with large value f is equal to p by 2 sine theta. Okay, from this you can easily make out why f should be equal to p by 2 sine theta, or 2f should be equal to p sine theta. Okay, and lastly you will have a mechanism where n will be greater than 0. So some members or the whole truss can move as a rigid body if C is smaller than 6 for space truss. Remember the degrees of freedom for a planar and a spatial for a plane truss. So degrees of freedom are not like necessarily meant to be 0. Many a times you want things to be n to be greater than 0 because you want to design a mechanism, and like a robots and any automation thing requires this n to be greater than 0. Okay, so I can perhaps show a couple of them. You have this as your so this is a mechanism. This part will clearly be moving like this. Okay, in this mechanism you can also have another variant of it. Okay, and say this, and similarly this is also a mechanism. Okay, so you should verify that this is a mechanism again. Don't leave or ignore anything which I write in red. Okay, just make sure that n, or show that n is greater than 0 in this case. Okay, so that's where the degrees of freedom of a truss discussion can be sort of stopped. And next we have to learn about how to find forces in members and joints. So when it comes to the our task of finding the forces in the members of a truss, there are two methods to go about it, and we'll be discussing both of them over here. Okay, so we have the so-called method 1, which is the method of joints. Okay, so what you have to do is take sections around each joint and draw the free body diagrams of it. Okay, take the sections around each joint in a truss, okay, and then draw the free body diagram showing all the pulling forces, and then apply the equilibrium equations for the joints. So FBD of joint, and then the equilibrium equations, that may be Fx equal to 0, Fy equal to 0, Fz equal to 0. Okay, and then you solve this particular equation. Now if any, I mean, you have to assume that all forces are pulling. Okay, and then you draw the FBD of the joint showing all the pulling forces, then apply the equilibrium equations. If any one of the answers comes out to be negative, like the force in a particular member, and it will be the same throughout because it's a two force member, if it comes out to be negative, then you have to take the negative value in all equations of equilibrium. Okay, and then just solve it again. Okay, so that will just make sure that the signs are all right. Okay, so always start with, say, joints which have only two or three unknown forces. Okay, that's just to sort of solve the unknowns or the easier things first. Okay, so if you have a planar truss, choose a joint which has only two unknowns. If it's a spatial truss, choose a joint which has three unknowns. Okay, and because in this step itself you will be able to get some answers which you can substitute in the later joints when you apply the equilibrium equations. Okay. So if you have the support reactions have been found from equilibrium equations of the whole truss, then at the end you can either take 3 or 6 equations of equilibrium are redundant and provide a check on the calculations. So that's also one can use for the constraints. Okay. So let me just show that with a diagram. So let me just write out. So you have, by writing the components of force is normal to the direction of two collinear members, okay, if any, so let me show that perhaps with a diagram first. This is a joint, so this is member 2, this is member 1, this is member 3, this is member 4, 1, 3, 2 and 4. So this is F2, F3, F4 and F1. Okay, so if you have a situation like this, then you can say that by writing the components of forces normal to the direction of two collinear members, if any, meeting at a joint 1, you can on this particular case say that if two pairs of collinear members meet at a joint where there is no load applied, so at this joint there is no load applied, then the forces in collinear members are the same. This would mean that you have F1 is equal to F2, and F3 is equal to F4. Okay, now let's take a case in which the joint has a load. So let me put that like this. Okay, 1, 3, 2. Okay, so now you have two collinear members which are forming a joint, and then there is a third member also. So F1 and 2 are the two. So I'm not writing the numbers now, I think it's quite clear. F1 acts on member 1 and so on, force in member 1. Okay, then the important thing is that the joint has a load which is P, okay, and this is in the direction of the third one. So let me just show that correctly. P acts in the direction of F3. In this case, the forces in the collinear members are equal, and the magnitude of the force in the third member is the magnitude of P. So F1 is equal to F2 and F3 will be equal to minus P. Okay, the magnitude will be the same, the direction depending on what is required. Okay, now in the other case, for example, if If P does not act, same case. Okay, in that case it remains the same. That means like P is equal to 0. So you will have F1 is equal to F2 and F3 will be equal to 0. Okay, so this will then be a so-called zero force member. Okay, fine. Now let's take up, if you have a joint like this, sorry, you have F2 so in this case clearly you will have F1 will be equal to, okay, so there is no other force other than these from of the members on this joint, and hence F1 is equal to F2. Similarly, if you have two non-collinear members meeting at a joint, let's say something like this, okay, so these you have non-collinear members, and in this case on the joint F1 is 0 and F2 is equal to 0. Okay, you can also have three coplanar, sorry, non-coplanar members meeting. So this is non-collinear and this one is non-coplanar. So F3, F2, F1, F1 is equal to 0, F2 is equal to 0, F3 is equal to 0. Let's take it as F1, sorry, this is collinear for F2, sorry, it is 2, F3, F4. Okay, now in this particular case you have two collinear members, clearly 1 and 2. Okay, and then two more members meet at a point with an external load acting on it, without any external acting on it, and the members are non-coplanar. So this is non-coplanar. 1 and 2 are collinear clearly. So in that case we will have F1 is equal to F2 and F3 is equal to 0, F4 is equal to 0. Okay. So let me draw another sort of a truss over here, just so that we know how to deal with the Okay, so look at this member 4 of this. Okay, curved member 4. So in this case, so this is B, this is D. Okay, so you have B, D, this is F4, F4, member 4, and then the joint B I'm trying to write, the FBD of joint B. So over here there's also a force Q. So this is B, this is F4, so on the joint always assume a pulling one. Okay, and then force Q, and then F1 and F3. F4, and then let me just sort of draw this. At this point we will have a normal, so this is the curved beam. Okay, part of the curved beam. So this will have a normal N, it will have a shear S, and it will have a moment M. Okay, this can be written as F4 F4. Okay, okay. So for this curve member in number 4 in this particular truss, this one truss, okay, so at any point you will have this normal N, S and M. This can be the resultant of this, I mean, which is shown through this, is just a single force F4. So this is the resultant of N, S, M. Okay, so this is how one can show the forces on this. Okay, acting at this along this line B. F4 acting along BD. So there are also, I mean, I'll show the reaction forces perhaps in a different color. So this constraint is at R1 and R2. This force is F. It's okay, I should not show this. This is R3, okay, because it allows a free rotation, free movement along the horizontal direction. So no constraint over there. This force is F given, and this P is given. Now the question is that you want to find R1, R2 and R3, okay, and they can be found, say, using MAZ is equal to 0, Fx is equal to 0, Fy equal to 0 for whole truss. Okay, okay, Okay. Now we can also apply fx. I should call the joints as well. This is C, this is A, and this is E. Okay. So fx equal to 0, fy equal to 0 for joints A, B, C, D, E. So they will give us f1, f2, f3, f4, f5, f6, f7. Okay, plus some check equations. Check equations in the sense you can check your whatever you have got and they will still satisfy the values over there. Okay. Now this is the first method, the method of joints. The other method which we want to learn over here is called the method of sections. Now the reason you want to start off with a few sections rather than the whole truss or each member individually is just because we know that out of say 1000 or 10,000 members of a truss, few of them are critical, okay, because they are more prone to fail just by experience or our understanding of the structure itself, and hence we want to find the forces in those members first, okay, and then later on we can keep on finding the other ones, but the ones which we think will fail or will break first, we want to find the forces in them first. Okay, and over there this method of joints will be very laborious because you have to keep on going to each joint and then do the draw the FPD and then find it, apply the equilibrium equation, find the forces. If they are negative, then check back the directions again and so on. So we rather than go for a method of sections. Okay, now there is one comment which is mentioned over here about method of joints which you should verify. Verify that M1 that for M1 the round of errors accumulate with each calculation. Okay, so this is something which you should understand. Where is this round of error coming in method of joints? If you have like a huge truss structure, why would you get round of errors? So try to answer this question that I have written in red. Okay, so method of sections is quite easy in the sense that you choose a particular section and then draw the FBD and apply the equilibrium equations and so on. Okay. So some of the tips of how to choose a section in plane truss. Again, this is a tip. The section should preferably not cut more than 3 bars with unknown forces. okay, which are neither concurrent nor parallel. Okay. Okay, so you can draw the FBD for them, and once you do that, you just apply, say, the equilibrium equations, which is the force balance and the moment balance, three equilibrium equations for a planar truss. Okay, so that is how easy it can be. So for example, in this particular similarly, I mean, this, if you apply to space truss, the number is 6. Okay, now if you consider this truss over here, one of the sections which we can draw is this one, x dash, which is shown in green color. Okay, now we can use this to find forces in members 4 and 5. How do we do that? Draw D over here. There's a P force acting. Okay, and you have this F4, F5. Okay, and then you have this E, which you have R3, and then you have F6. Okay, this is how you had cut, and this was there. Okay, now you can find the forces in members 4 and 5 of this truss by taking this cross section. Draw the FBD of the part to its right. Okay, and use this MCZ. Okay, C's is equal to 0, C is this particular point, and Fy is equal to 0. Okay, once you do this, you should be able to get F4 and F5. Okay, so that's how one can solve. So this is how you can solve the method of sections using the method of sections, and clearly you will have to have some experience in your correct choice of using a section. Okay, if you choose a wrong section or a section which doesn't really help you, then it will be as cumbersome as the other method. So one has to be slightly careful, and that wisdom comes from experience in trying to solve many problems. Okay, let's now define a simple and complex truss. Okay. So let me first draw it with a diagram. I think that would be much better. Okay, so P, E, F, and this is C. Oh, sorry, this is not fixed. There's a roller over here. Okay, then you have A, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and this is fixed. H, G, sorry, this is G, this is 40 kilonewtons, this is 3 meters, this is 60, this is D. Okay, seems I have drawn all of it. So this is a simple truss. It is plain clearly. So I'll define it I'll define it both for space and plane, so that in one definition we can have both. A simple space or plane truss is formed by a basic tetrahedron in space and triangle in plane with 6 or 3 bars and 4 or 3 joints, which is just rigid. We have learnt about what a just rigid is before, and successive addition of 3 non-coplanar members to successively form other j-4 or j-3 joints, and having C is equal to 6, three independent foundation constraints. Okay, so I have drawn a planar one. You can also have a spatial one. I'm not drawing, or perhaps I should, just for the sake of it. D. So this is a simple space truss. Okay. Just because it is just rigid, so we always, there is always this motion as a rigid body as a whole. Okay, so the degrees of freedom, etc., are 3j minus b minus c is equal to 0 for a space, and clearly it will be equal to 2j minus b minus c is equal to 0 for a plane. Okay. So you have the triangle, for example, ABC over here. Okay. The simple plane truss is formed by triangle ABC with joints ABC followed by other joints in the order D, E, G, F, H. Okay, and one of the things which you should note, even though we say that a simple truss is formed by a basic tetrahedron or a triangle in plane, it is not necessary that it will only be formed by triangles. Okay, it's just to understand better we put it like that, but it's not necessary. And you may have an example, say like this, which may not only have triangles. Okay, so this is also a simple plane truss. Okay, now to be able to find the reactions at these foundations, okay, you can first of all apply the equilibrium equation to the whole truss. There will be 3 equations. Okay, and then to find the individual forces, you have to either use the method of joints or the method of sections. Okay, so let me draw for example, you can have 2 sections drawn. Let me show that. One can be something like this, x, x, and then the other can be y, y. Okay, so you can separately take up, like first take up this section on the right of xx, then take the section on the sort of left of yy and draw the relevant free body diagrams, and then you can apply the equilibrium equations for this. Okay, so this is something which you can follow, and using the solved examples from the textbook you will be able to understand this concept slightly better. Okay, so this topic in brief is better learned using examples. Okay, the method which we have already discussed, but let's now move. So the last topic which we want to discuss under this heading is beams. Okay, and how do we define a beam? A beam is a member with small transverse dimensions compared to length. With bending moment and shear force as the predominant internal actions. I think we had already defined it, depending on what the predominant internal actions are, whether we call it a column or a beam or a strut and so on. internal actions. Okay, so they have lots of use in, say, roofs, okay, of the room in which perhaps you are sitting right now, and then you have pipelines, okay, or even, I mean, things which are not necessarily a beam as such, but we treat them like a beam, as I had already sort of, let me just show that once. Think of it like a dam, okay, which has this as your head, okay, and say it's not allowing any water to flow right now, or allowing very little water to flow, but let's assume that it's stopped now, no discharge of water is over here. Now, as you know, the force which will act on this sort of wall over here, it will be atmospheric, and as you go deeper, it will increase with the depth, okay, like a rho g h sort of a behavior. Now if you invert this, okay, you have a load on this which looks like this. So this can also be seen as a beam, okay, even though it's not a beam element as such used in the things around us directly, but it can be modeled as a beam. So beam is a particularly important element of engineering around us, and hence we study it quite well. You are all studying it in first year itself, and the ones among you who are in relevant disciplines of civil or mechanical engineering, they will study in slightly greater detail with all its glory and assumptions and shortcomings as well. Okay, so let's take up some of the examples of beams. I mean, how can they be? Okay, so one, for example, you will have so this is fixed end, then this is a uniform loading, say 2 kilonewtons per meter, okay, and this is intensity is Q, and this is the free end. So there is a free end over here, that means that there is no reaction, okay. You can also have a roller support, say something like this, in which, okay, so this is a roller support, okay, so the reaction in this case would be, say, in the normal direction, because it allows a free movement in this direction, okay. You can have a pinned uh, end, okay, so if you have, say, something like this, okay, and for this case, okay, this is the pinned end, so you can have this R1, you can have R2, okay, and then you will have, say, C1, because it allows neither a translation in the horizontal or vertical direction nor a rotation. So that's why this R1, R2 and C1, all of it have to come, other than the usual P, F, C and this Q loading, okay. Over here for the roller, I can draw it as R N hat, then again P, F, 2 kilonewton per meter, 2 kilonewtons, okay. Okay, hold on this, and then you will over here you will say you can have a pin. So pin will only allow R1 and R2. This is a fixed end, so it will not allow a rotation, but a pin, as you know, allows a rotation but not any translation. Okay, so this is how you can have, I mean, these are some possibilities, and there are other situations as well. One name which you should definitely know at this point, at least two names, is that if one end of the beam is fixed and the other is free, then it is called a cantilever. If one end of beam is fixed and the other is free, it is called a cantilever. I should write it. This is very, very, very important for you to know. When people ask you something about beams, they will not explain what a cantilever beam is, irrespective of your branch or discipline or your year of study. So please know this word very carefully. Okay. Similarly, if you have a beam with two supports which are either pinned or on rollers, is called simply supported. Okay, so either pinned on or on roller, it is called as simply supported. This is again something which you should be knowing. Okay. On the other hand, you can also have beams which are like this. Okay, fixed beams. So these are fixed at both ends. And then you can also have okay, if you have something like this, you have a beam with two supports and extending beyond one or both supports, okay, as evident from this diagram. This is called a overhanging. Now, one of the sort of usual expectations is that one would be able to draw the bending moment, or draw, or at least write the equation first. Bending moment M of x, shear force S of x, and axial force N of x, okay, versus x. Okay, so these plots, plot meaning you draw it on a graph, they are called the bending moment shear force and axial force. Diagrams. Okay. So you already know this, that the slope of the, we have already seen that the slope of nx curve is actually equal to minus qx. Similarly, the slope of sx curve is equal to minus qy, and the slope of mx curve is equal to minus s minus m. It is equal to minus f if m is equal to 0. So we have already seen these before when we were discussing bars, and these are very important in trying to draw the plot. Okay, so you may have an expression, say for n or m or s, but you have to then take a derivative of that and then you can draw the diagrams. So if you have, for example, you had already seen equations 4.16 before. Let me show what those were. Okay, so 4.16. So if there were, so for any part of a bar, we had derived dn by dx is equal to minus qx, ds by dx is equal to minus qy, and dm by dx is equal to minus s minus m. Okay, this was 4.16, and this was true as long as there was no discrete load on the segment, no discrete load. Okay, so if you integrate it, you should get n of x2 minus n of x1 is equal to minus of x1 x2 qx dx. This is minus of area under qxx diagram. Okay, or this is the minus of load along x over x1 to x2. Similarly, if you integrate the second one, you get something like this. Qy of x diagram minus of load along y over x1 to x2. This is 4.56, and finally m of x2 minus m of x1 is equal to minus of x1 x2 s dx minus x1 of x2 m dx. This is minus of area under Sx and Mx diagram. Sorry, this was 4.55. Okay. Okay, so there are two ways you can sort of draw this. One is that you integrate the differential equations of equilibrium. Okay, these are the differential equations of equilibrium. Okay, and then the second method is that you consider the equilibrium of a part of the beam. Okay, so just a case, if you have a beam say like this, and at A1 you have say this P acting, then A5, then you have sort of A2, A3, A4. So at A3 you have say C acting, A2 Q acts from Q is a uniform loading, acts between A2 and A4. Okay, and A5 is your roller joint. So this is your Y, this is your X. Okay, so you can break them down into separate parts. So for example, if this is A, you can have from A to X such that X is less than A1. Okay, so you are somewhere around here. Then the other you can draw is from A to X, where A1 X is greater than A1 and smaller than A2. So between this segment, okay, and then you can have say another, I'm not drawing the diagram, but you can have another segment which can be, let me just remove this, X greater than A2 and smaller than A3. Okay, lastly you can you can have X greater than A3 and smaller than A4, and lastly A4 X A5. So for each part, okay, each part you will apply these equations 4.45 to 4.46, and then you should be able to do the free body diagram, then apply those equations, and then eventually plot the bending moment or shear force diagram. So once you have those things, you should be able to draw some useful results which you have is ds by dx is equal to minus qy, dm by dx is equal to minus s of x naught, and this is when m is equal to 0, plus is equal to s x naught minus f phi naught, and m x naught plus is equal to m x naught minus m naught. Okay, so you have to see the solved examples in the text book. Okay, this is better learnt using solved examples, just like the previous case. Okay, so that is where we end our discussion on beams. Thank you.